Hello. This is a very interesting game theoretic problem that I came across. So let me describe to you the game without further ado. There's a large circular table, and there are two players, A and B. Player A and B take turns to play this game, and the idea is that each of them place a coin down on the table, one turn at a time. So say player A starts, he places one coin down on the table, player B plays second, places another coin on the table, then player A plays once more, places another coin wherever he wants on the table, player B plays again, and so on. And the game continues till a player is unable to balance the coin on that table anymore, and that player loses. Now, of course, there's some rules, like you can't stack coins one on top of another, and you cannot put the coin on its thin edge, on its side. It has to be laying down on the table. Although it can be partly off of the table. All that matters is that it has to be on the table flat. So the question is, if you had a choice to play player A or player B, which one would you choose and why? So if you want to think about this problem now, would be a good point to pause the video and give it some thought. Okay, so one very interesting aspect of this problem is that people who studied math tend to be able to solve it like that. And people who may be much more intelligent, a lot of my friends who I would feel are just much more intelligent, if they're not trained to think mathematically, they would just not get it. They would make very intelligent arguments and would go down wrong tracks. So there really is a very interesting, unique way of thinking about this problem that reduces this big complex problem to actually a very, very simple solution. But let's look at some ways of thinking about it and how we try and approach it. Now it would be another good time to stop the video and think about not a solution, but ways that you would arrive at a solution, different methods of proof. All right, so one interesting idea that many people come up with, even if they don't solve the solution, physicists in particular, is edge cases. Notice I never said anything about the size of the table or the size of the coin. And when I first heard this problem, the first thing that came to my mind was, don't I need some information on the size of the table and the size of the coins? For example, there may be a table that's able to fit 2 coins, and there may be a table that's able to fit 3 coins. Wouldn't the answer differ then? Wouldn't you rather be A or B, depending on which table you had, assuming the coins were the same size? So, clearly the answer is no, otherwise I wouldn't be asking this question and wasting your time. So let's think about a very simple edge case. What if the table was small? What if the table was smaller than the coin? It probably wouldn't be, but I never gave any restrictions. So what if the table was this big and the coin was this big? Then really you can only balance one coin on that table, right? So you would really want to play first. You'd put that first coin on the table, and you'd win because B wouldn't be able to do anything. You can't stack a coin on top of another at all, and there's no table for him to play with anymore. So if there is an answer, and of course there is because I wouldn't be asking this question otherwise, you clearly want to be player A. You want to play first. So that's an interesting idea that gives you the answer. This edge case allows you to know that you want to be player A. But it's a whole different ballgame to actually prove that. So if you want to think a little further now that you know who you really want to be, now's a great time to stop the video. Okay, so there are many different ways to look at this. One interesting idea that a lot of people, who are good at reasoning out, who I talked to and actually didn't arrive at the solution, but the logical, clear thinking would explore the idea of the table being able to contain an odd or an even number of coins. If you want to explore this idea further without my going on, stop the video now. Alright, so now that seems like a good idea at first. Why? Because just imagine if the table could contain an odd number of coins. Then you'd want to be player A, because just imagine if the table would contain 3 coins, right? Player A would play 1, B would play 2, A would play 3, and he's 1. If there's an even number of coins, you want to be B. because B would win. But there's what do you see the problem with this idea? It's the problem with this idea is that sure, the table may be able to contain an even or an odd number of coins with perfect play, and by perfect I mean you're filling up as much space as possible. So if you were to put the coins snugly in their correct places so that the least space is wasted, then there may be an answer that the table can hold an odd or an even number of coins. But given that the players can play wherever they want, the same table may in some cases be able to hold an even number of coins, in some cases an odd number of coins. So really the idea of looking at an even odd is, while it's a good idea, it doesn't quite work here because there can be different configurations on that same table, some containing an even number and some containing an odd number. So that doesn't really help us. Another interesting idea that often comes in handy is that of contradiction. You assume one player you would like to, say play first or play second, and try and derive a contradiction from that. And in this case, you have the added advantage of knowing the answer. You know that you really want to be player A, you want to play first from that edge case. So another idea would be to try and assume that B would win in all cases if he played perfectly, and try and reach a contradiction from that. If you want to think about this idea further, again, now's a good time to stop the video. So I apologize if you spent a lot of time on this. It turns out that contradiction doesn't work here as well, because this is a very complex problem, as you can see. There are infinitely many configurations, well, not infinitely, but a huge number, exponential, of configurations of coins on this table. And contradiction is not going to help collapse that enormous complexity to a simple solution, because there really is no way to say, okay, let's assume B wins. Where do you go from there? It just doesn't work in this case. So what we really want here is an algorithmic proof. In other words, we want to give an algorithm. We want to give steps for player A to play. We want to tell player A how to play so that he can win. And then we have to prove that that strategy, that idea of playing, that way or method of carrying out his game actually does win. And now another very interesting idea emerges here. A lot of people who think really hard, come up with very good ideas, but wouldn't get to the solution. When you actually ask them the right questions, and walk them through it, they come up with all the answers by themselves. And so it's another very important lesson is, asking the right questions is very, very important too. I mean, people say that there's no such thing as a stupid question. That is true, but I mean, there is a thing such as a good question that really gets to the heart and crux of a matter, of a problem. So asking the right questions, or wherever it is in life, is I think a very valuable skill too. Not just asking questions, but the correct, relevant, pertinent questions that go right to the heart of the matter. So let me try and walk you through it. Keep stopping the video as you feel necessary, and let's see if you can solve it. And I'm reasonably confident a lot of you will. So we want an algorithmic proof. We want to tell player A what to do. So my question to you is, you're player A, you know that player A is going to win with perfect play. He has to play. You have a coin and you see this circular table in front of you. You have to put the first coin down, right? Where is the one place on this circular table right in front of you that you want to place your coin down? Sure, you could place it anywhere, but where are you going to place it? Where do you want to place it? Where does it strike you to place it? Think on this for a bit and stop the video if you want. If you thought the center of the table, bingo, you're right. Because, I don't know, everybody I ask, I haven't met a single person who, thought about this problem and was like puzzled or everybody says, some people say confidently the center, and some people say the center with a question mark at the end, but everybody says the center. And why? We'll come to that later, but it's really, what is that to a circle? There's this radius and there's the center, right? The center is kind of unique in some sense. Alright, so A put his coin down in the center, and now player B is going to place it somewhere on the table. wherever we want. Because we have no control over what player B does, right? So let's assume player B puts it here, right? And now is the crux. An algorithmic proof would be crazy if you had to give an answer for what everything B does, right? So B can really put it in so many different positions, and it would be hard to come up with a response to all of that, and further the complexity increases in the next move and next move and next move, and it goes on and on and on. So really you want an answer that generalizes, that is a general response to where B puts it. So given that you have this table, you've put one coin in the center, B's put one coin at any point, you have no control over that. What do you want to do? What does A want to do? Where does A want to put his coin? Think about this. This is a great time to pause the video. So this step is a little more tricky than the first step, where you put A in the center. And I've got 2 or 3 different answers, but a lot of people do get it at this point. The idea is an interesting idea, way to think about it is, notice that I gave you a circular table. I could have given you a square table as well, a rectangular table too, but I gave you a circular table. I could not have given you an irregularly shaped table, something like that. That would not work. Why do you think? What does a circle have that this does not have? Exactly, symmetry. A circle is symmetric. In fact, the circle is the most symmetric shape that you can get. So really you want to use symmetry in the problem. So where would you place the coin using symmetry? Exactly. You take this as like an anchor point and put your coin, next coin, symmetric to where B places coin with respect to your center coin. The only other answer I've really got is some people say put it in the middle of your first coin and B's coin, and that won't work. But why is this idea so powerful, this symmetry idea? Think about it, pause the video and explore this idea further. Absolutely. So the idea is that with respect to the center point, there are always going to be 2 symmetric, for every given point there's always going to be a symmetric point. So given that the center is fixed, for any other random point in the circle, there's always going to be one and only one point that is symmetric with respect to that center point of that first random point that you picked. So the idea is that anytime B can put down a coin, A can always put down the coin in the symmetric position, because if that position wasn't available for A to have played, then that position would not be available for B to have played, just given the way we're carrying out the game. Now this idea may be very intuitive and may make sense and click for you at once. There are a couple of people who actually still don't buy this argument. So I wouldn't say it's trivial, but try and convince yourself of this fact. Think about it, explore it, and with a little time it should be crystal clear why this works. There are always, with respect to the center, 2 symmetric points. Given one point randomly, there will always be exactly one symmetric point. So these 2 points form a pair. And given that there are 2 players and they keep taking up those symmetric points, every time B plays, you kind of take up that opposite symmetric point. And if B can play, you can always play, because this other symmetric point should always be available. That's the argument. Now, and so I said we would come back to why we placed the coin in the center in the first place. What does that do? Why couldn't A have played second and keep carrying out the strategy? The idea is that the center point is unique in that it's the only point that is symmetric with respect to the center to itself. It's the only point that is its own image with respect to the center. So if you imagine this as a mirror, right? You have this point, this would be the reflection. But if you have a coin here, the coin is its own reflection. So in other words, A plays this waiting move. He takes control of the center. It's much like a chess game where you want to take control of the center, and you often want to make a waiting move so that your opponent plays, and then depending on what your opponent does, you can pounce and attack him accordingly. He gives away something by playing. So usually in games, like even chess, you want tempo, you want to make the move because moves are valuable. You want to gain speed, you want to gain development, you want to put your coins down, cover up the table. But in this case, there's this very interesting idea of a waiting move. You want to wait to see what your opponent does so that you can respond accordingly. So I really thought this was a fascinating problem, and hope you enjoyed it. What's really amazing about it is how it's a really, really complex problem if you think about it. There's so many different configurations of coin. But with a simple argument, you can reduce that enormous complexity to a very, very, very simple idea. Thank you.